today is one of the most important lecture in this online course, Production Performance Analysis and Forecasting. In the last three lectures, first three lectures, we talked about how can we upload the data, and then how can we analyze the data correctly by using different plots for our production and see the performance, as well as using maps to see the bubble map and the contour map and the grid map. All of these plots and maps, when be integrated together, give us a big vision about our performance of the production. And after that, the main objective of this analysis is to go with the forecasting and determine how many oil is remaining in our reservoir, and we need to know the reserves. All of these information can get by different methods. We know an volumetric equation start initially in the reservoir, determine how much the hydrocarbon in the reservoir. Then with time, after we start the production, we can use a different method called material balance equation. This method is very powerful method, help us to determine the hydrocarbon in place, and always we can use it to predict the water influx. Then we can predict to the production in the future. And there's another method called decline curve analysis. This method, it's one of the most important methods used to determine the reserves. This method is very helped, especially when there is at the end of the lifetime of the field. That means decline when the production dropped in our reservoir. So this time, it's when we see in general the production initially is increased, then stabilize for some times, maybe 10 or 20 years, depends on the field development plan. Then when the pressure is dropped and still dropped, the production will be decreased also. So after the production is decreased. Here is another different point we can start with by applying decline curve analysis to determine the reserves and determine the ultimate recovery and how much production will be produced in the future with this decline. So today we will introduce another different method. It's called decline curve analysis. This method is very simple. It's a graphical method. We will see in the next slides what's the types of decline curve analysis and how can we apply it practically and to determine the reserves and the production remaining in our reservoir by our case study that we use it in our course. As I mentioned here, this method is a graphical method, means we have x and y axis different variables give us a good indications about the forecasting by extrapolate the performance. The extrapolate means we have to, depends on the line we produced, and we will see that we can predict to the future by the same as data dropped in the reservoir. So the main and fundamental objectives of the decline curve analysis is to determine the remaining oil reserves. And here, what's the mean of reserves? The oil or gas which can be produced from our reservoir economically, and that's the most important thing. The mean of economically, it's the fundamental word used in reservoir engineering, especially when we mean by reserves, that means the oil or gas can be produced. If we cannot produce it in this right now, that cannot be named as a reserve. It will be called original reserves, but here I mean by remaining oil reserves, the oil which can be produced in the future economically depends on the type of reserves, as well as depends on the technology available in the field. That means in our case we just only work with the natural drive mechanisms, so we don't add a water injection or gas injection in our reservoir. All of the reserves will be from natural drives. And after we determine the reserves, we can determine the ultimate oil recovery. The mean of ultimate oil recovery is the maximum production, the maximum hydrocarbon produced from our reservoir, which is after this point, after this recovery, we cannot produce any hydrocarbon from the reservoir. So the mean of ultimate recovery, the maximum oil production, the maximum recovery from our reservoir. We know recovery factor, it's equal to the production from our reservoir, the maximum production divided by the total hydrocarbon in place or original hydrocarbon in place. When we divide them, it's equal to the recovery factor called ultimate. And the last point in decline curve analysis is called remaining production life of well, field or reservoir, etc. Decline curve analysis, and that's one of the advantages, can be applied for well to determine the reserves, to determine the ultimate recovery and the remaining production for the well, or can be used for the total field, all the wells together, or you can use it for each reservoir. So we will see in the next part how can we apply this decline curve analysis for the field or well, or and that's the great method. Material balance and other method to determine the reserves cannot be applied for well. We need to work with our reservoir. But decline curve analysis, because it's just only need the production data, only the production data, that's the data we need to apply the decline curve analysis over time. But in material balance, we need BVT, we need some additional data, production and pressure, all of these data needed. But in decline, we don't need pressure, we don't need other fluid properties, for example BVT, beta oil, gas, RS, other we don't need it in the equations of decline curve analysis. And that's advantage for this method, because we know in BVT and other properties, for example reservoir properties, it has some uncertainty due to a high region in the reservoir, and we cannot determine one value represent our reservoir. So that our results in material balance and other methods give us also the simulation give us we have high uncertainty in these data. But decline curve analysis, it's applied just only we need the production data. Production data, we means if we are to determine the oil reserve, so we need just only oil rate, and we know the rates and the production, that's the required data, and that's the consistent data, because all of the oil comes to the surface, so we can measure it by using metering there, and we can give us and we can confirm these data actually for the field or the well. So these are most important three decline curve analysis objectives to give us from this method. Here is the most important thing. We have some assumptions and limitation for this method. You must be carefully here and understand each point before apply decline curve analysis. Here is a curve fit of the past production performance is done using a certain standard curves. We will see the curves can be applied, the types of decline curve analysis. We have the three types. So to get a good indication or to get a good result from decline curve analysis, must the curve fit for the best production performance. That means we have to enter, for example, 20 years of production data that's in the past to help me to get a good result in the future. By applying the best curve fit, we will see that also in the practice. How can we apply and match the past production performance must be done. That's the first point. Then we can depends on the one of the curves that match with our past production. It will depend on the future. After that, after apply the curves with our curves for this decline with our case, then we can extrapolate to predict the future performance, and also we can estimate the recoverable reserves, the mean of recoverable reserves, that's the maximum production. So if I predict the future performance, we depends on the curves here. I will see the end of the production time that will give me the total oil production from our reservoir. So that means when I divide it to the total or the original hydrocarbon in place, it will give me the recovery, ultimate recovery. And there's another point. Conventional decline curve analysis can be used only when the production history is long enough that a trend can be identified. Yeah, that's important thing. We cannot apply decline curve analysis if just only we have 5 years of production. That means maybe if the production is annual, that means we have 5 points. Maybe the 5 points when I plot them cannot give me the curve cannot be identified. So I need to long production history of drop of the production to see the trend, and we can apply one of these curves. And there is assumption is very important here in decline curve analysis, which is very important before we apply that. The first assumption is whatever causes controlled the trend of a curve in the past will continue to trends in the future, and that's the very important thing. For example, if the reservoir initially start our production for 10 years, the first 10 years of production produced naturally, that means it depends on the natural drive mechanism in the reservoir. Then after 10 years we use it in the field. For example, another different technique, if for the well after 10 years we apply the artificial pump, ESP or gas lift, so the production will change. That's the different from the past 3 or 10 years in the past. These years produced naturally, and we see the drop in the pressure, so we can apply decline curve analysis because the production also will decrease. But after 10 years, the production again, after apply artificial lift, the production will increase. So here we cannot apply decline curve analysis because the past, what they can control the past is not the same in the future. So if I change the management for our reservoir or well by changing the drive mechanism, so we cannot apply this method because what the past that control our production is not the same as in the future. So these different two methods cannot give me a good indication to extrapolate these data to the future. So that's the assumption is very important in applied decline curve analysis, many of engineers cannot understand or realize these points, so apply just only decline curve analysis at any way, but that cannot give us a good indication. So what the control in the past must be continuous to the future. And the extrapolation procedures is very important, depends on the empirical, some empirical correlations. We will see that in the next. Depends on the Arbus equation, and we will see the theoretical of these methods. Actually, the Arbus equation does not have a physical mean, because it tried to define the curves with different. We will see that because it's just only we have to apply the equation that represent our curves for each of one of the for each curve we have for each type of the decline curve analysis, and give us an equation applied at any one of the curves. The last point, the reserve estimation obtained by decline curve analysis are limited to those recoverable under the existing condition. As I said in the first one, the reserves depends on the condition existing in our reservoir. So maybe we can get a reserve that the total produced from our reservoir, but the existing condition means if we have a natural, but cannot give us a recoverable if we change the condition for our for the technology, for example, or so that will change with time. Decline curve analysis cannot be applied across recovery phases. What's the mean? That's the point I talked about, and there is another example. If initially a water flood would define to change the cause that control the trends of the the curve too much. Here that mean if we have a water flood, for example, if we produce it from initially and then use the water flood, so the changes will happen, and we will see that on the curves. So cannot give me a good indication about the field. So the first step is to analyze the data production for oil rate. Then we see our result. Decline curve analysis should be applied for reservoirs under boundary restricted flow conditions. The decline curve analysis must be we know the boundary of our reservoir, and we know that all the production comes from the production of the boundary. That's mean if we don't reach to the boundary of the reservoir, so you cannot apply decline curve analysis, because that doesn't mean you produce from the total reservoir, so all the estimation for reserves and the prediction would be wrong. There is some restrictions here. This method is not based on physical principles. As I said, the Arbus equation don't have any physical principles. So it can only be applied as long as the mechanical condition of the well completions protection method are not changed. To it work with the wells and the reservoir, just only we need to consist the existing conditions, so we don't need to change the completion for our for example, if you have you apply reperforation, so we use the production, so the decline curve analysis cannot help me after apply another different completions. Also the production method, as we talked about, assuming that the drive forces in the reservoir means the drive mechanism are not changing during the time. That's the assumption. It's very important. We don't need to change the drive mechanism for the reservoir, especially when apply decline curve analysis for the reservoir. So if you change the drive mechanism in the year after in production some years by apply water injection or another method, so the decline curve analysis cannot be applied and will not get a good results. here there is three types of decline curve analysis methods. The three methods, it's first of all is exponential and hyperbolic and harmonic. These three methods we will see each method here have a mathematical equation applied for a specific condition to give us prediction performance, to predict the future performance and estimate the reserves. It's implicitly assumed that the factor causing the decline curve continues unchanged during the forecast period. Yeah, again, the same assumption here. Depends on the reserve condition and operating condition. Reserve conditions, that mean that don't change the drive mechanism, and operating condition means don't change, for example, the technology we have and any other operations run on the surface for the field or wells. So these must be fixed for all the time. As we talked in the first slide for this lecture, the objectives of decline curve analysis to production forecasting and reserve estimation during a primary production. Decline curve analysis can be applied to basically for any well or reservoir. Yeah, that's important. As we talked, decline curve analysis applied can be applied for wells or a reservoir. Why? Because it's just only depends on the production data, and the production data is that's always available, and we have a good data, as well as it have more confidence than other data. Nowadays, decline curve analysis is applied by different tools. We can apply it by using Excel spreadsheets. We can also apply it by another different software. For example, one of them is OFM. So we will see that an advanced decline curve analysis in today's production database greatly speed up the application because we use auto decline fitting. Yeah, we will see that in OFM. We can apply that more easily in just only in second by click on this some points. We will learn how can we apply this technique to give me a good result for determining the decline curve analysis. Again, just only we need one data. It's the production data over the time for a long time of production history. We have two types of types of curves used to decline curve. One is we will use it that oil rate or rates for oil or gas or water depends on the phase we need to apply versus time. That's the first plot we will generate it, and the second plot is rate versus cumulative production. Each curve here, each plot will give me a good some indications must be completed to each other and give us a good vision about the production performance and the reserves and the ultimate recovery by applying the plots. And there is another curves that these the two curves, that's the main curves, and we have some other curves. It's by applying the water cut versus time or water cut versus cumulative production. This plot shows the three curves here. These three curves represent the three types of decline curve analysis. We can see the relation is between rates versus time, and we have three colors here. The red one is exponential method. That's the first type of the decline, and the green line is represent to hyperbolic, yeah, and the blue line is represent to, sorry, here it's harmonic. When b equal to 1, we will see the factor b factor, it's harmonic. So these three curves changes and depends on the mathematical equations for each one of them. And that's the first. Initially here in the time we have to add some data, the production data for many years, and it depends on these data. For example, if we have for example from to 6 years of a production, and we can see and can be defined which the data matched with which one of these curves, then we can depend on these curves to forecasting or to know the production after 15 years. Depends on one of these curves that match our data. And the assumption of that, again, as we talked about and we explained it, what's that control the past future, the past production performance. That means if we in this 10 years or 6 years in the past production, if we produce it naturally, so that will continue to the future. In other words, if these 6 years of production produced by natural drive mechanism, then after apply another different method, artificial one, the production, the rate here will not decrease, it will be increased again, so we cannot define which the curve will continue to the future. So the first assumption with that control the past production will continue to the future. All these types of decline curve analysis, these methods have each equation, but the main equation from this, or the basic, is by applying the Arbus equation. This Arbus equation, this is the main equation we have for this method. As we explained, the Arbus doesn't have physical principles, so it just only gives us by applying 3 equations to model the production declines without any physical mean. So here we need 3 important points to apply the decline curve analysis. We need an y-axis, as we define it here, we need the initial oil rate or initial gas or water, depends on the phase. So that's the first point. The oil rate will be in y-axis, so that's the initial point Qi. We can see in this equation the initial production, initial rate. And the second point, we have to define initial decline rate. Initial decline rate, that means for each month or each year how many dropped in the production. It's over time. So that's the decline, means the slope, because in oil rate versus time here we can define the slope. So how many production drops due to over time for year or month. And the degree of the line that changes, it will be equal to b. B, it's changes from, depends on the case we have. So in one of the first method, the value of b, it will be equal to 0. We will see that in harmonic. For exponential. Exponential actually is not defined like this. It's equal to represent to the straight line, and the b will be equal to 0. That's the assumption. We will see that. Yeah, this is the main Arbus equation. We use it, and all of these methods, all of these types of declines comes from derivative from this main equation. Arbus only indicates the exponential decline b equal to 0 is most common, and that's coefficient b generally ranged from 0 to 0.5. That's mean here, but if we need to apply the exponential, the b will be equal to 0, and we can get another equation by cancel this be 0 and this will be 0, and the mathematical equation will change it, and we will see that clearly always don't accept exponential behavior during depletion. After some times, not all the curves, not all the, we will explain that more, the exponential method is not shown. The pressure or the production drops as a straight line. It will have some curves, so that will change it, depends on the B here. And here is our case. In many cases, the hyperbolic decline is one of the methods where rate versus time is better for more than exponential solution. We will see that. So we can see here these red points represent to our production performance, and we can see this decline in the production rate. So here in this case, and that's from O of M, after apply the method of hyperbolic because we can see it's decrease here and then go like this. So we can apply the decline for the hyperbolic, which is represent and match to the actual data. And here's the note for interpretation. Hyperbolic decline is observed when reservoir derived mechanism is solution gas cap or have gas cap drive or water drive. Observed change in the shapes of the curves from Cartesian to logarithm. It's very helpful in identifying the type of curve. In some cases we use here in y and x, and y use semi-log plots, but if I use the Cartesian in y and x, maybe the curve cannot be defined more clear. So by using semi-log, that means log for q, and the time will be Cartesian, it helped me to identify the curves like one of these curves here. And two sets of curves are normally used while analyzing the production data, as we define it here is the flow rate versus time. It gives me a good future production directionally. We can see, for example, this is the basic data we have, and from this plot, the hour rate versus date, it gives me the production, how much oil will be produced in the future depends on these data. So if this line represents this point, so after 1994, we can, depends on this curve, depends on the one of these curves. This curve is represent to hyperbolic, so we can depends on this line to predict the production to the future here by using oil rate versus date. And if you use the second plot, flow rate in y-axis against the cumulative oil production, it's very important to give me an indication about recovery reserves and the ultimate recovery called EUR. And when we reach to the specific economic limit, that means the oil we produce it economically. After this point, we cannot produce any oil because can different changes in economic conditions. So maybe we produce less oil, and this oil cannot help me to, after we all of these operations that cannot be used because it's not economically, and we produce it with high costs. Now we need to explain some theoretical about the first type of decline curve analysis. It's exponential method. Exponential method assume here b equal to 0. This is the basic main information, main equation for the method of Arp's equation. Here when we apply b equal to 0 in this part and this part, so this equation will be like this. Here the current production rate that's changed with the time, and what we need here in the right side of this equation, we need initial production rate, as we define that's the start of the production. So this is data is available for us, and what else we need? We need here delta t, nominal decline rate. It's constant. That's for a nominal decline rate. Maybe we can use it as a month per production per month, or yearly, depends on the data we uploaded to data we for this method. If we enter or use the monthly production, so the nominal decline rate, it will be constant, and it will be rate per month. Or maybe we can use annual year, and here the time cumulative, and since we start the production, and we will go to the future. This is the simplest equation for this method, because d is b equal to 0, and we have another different theorem. It's called effective decline rate. That's d constant over time, and the log, after we plot the log rate versus time, and we say it's a semi-log plot, because if we use a Cartesian plot, we cannot define the curve, and will not be very clear. So for the exponential, after apply this method, it will be a straight line on a semi-log plot, and we will see the example. And if we need to use a rate versus cumulative, it's also a straight line on a linear plot, shows below here. That's the equation. After from this equation, when be integrated this part, the oil rate to be time 2 to time 1, it will give us a cumulative total oil production over time. And that's the example of exponential method. That's the data for well H18. We can see here in y-axis is oil rate log, and that's the time here. From this plot, as we define it, we can use it to predict the production, oil rate production in the future. So after apply the method of decline of exponential method, we can see the matching between our data and this line. It's represent to the exponential, and the exponential always will be like this. It's a straight line. Our data here from 1982, that's the initial of a production, and this line must be adjusted to be at the initial point here. We can move this and all of them from this point to this point to be like this, but this is the best match for our data here. We can work with all of them, and we will see that that's the exponential method, and we can change and control for this line to be adjusted with our data, and we will see that in the practical. And the exponential method, it works with our oil reservoir above vapor point, and or in down dip wells with a gravity drainage. We can use it for this drive mechanism, or use it for solution gas drive. Also, and we can apply this technique in gas reservoirs and high reservoir pressure, abnormal pressure, and also we can use it for our wells with liquid loading problems. It means the water. Also, we can use both for oil and gas reservoirs protection with a small drawdown relative to the reservoir pressure, or tubing limits width. Here we can apply it also for small decline in the production rate, and will give us a good result for the exponential method. Here we need to know more about nominal and effective decline. We see here we have in this part we have a nominal decline, and the capital which represent to the effective decline. So what's the mean of decline rate? The nominal decline rate is d small. It's defined as the negative slope of the curve represent the natural logarithm of the production versus time. Here's the after we apply for in the exponential or any type of declines. That's the main equation for nominal curve. It will give us, because the relation is between and y-axis log q over time divided by the time, so the slope will be negative for this nominal decline. Nominal decline is continuous function, and it's the decline factor that's used in the various mathematical equations related to the type decline curve analysis. Every type of decline analysis, we have a nominal decline, which is represent to the slope, or but this is changed with time. We can see here if we applied the difference between each 2 points to give us a slope value. That's the continuous function. It's a changed, it's a dynamic, but there is another for exponential decline. It's a constant with time. Why? That's because it's a straight line, so at each point the slope must be constant. And the second part of effective decline curve fact is D is a stepwise function that's better agreement with the data according practice. It's a drop in the production rate from initial to any oil rate over a specific time period. We can define this effective decline rate equal to the difference between initial and another different point of production divided by initial oil rate or initial fluid rate. So that will give us an effective value for decline. Effective decline, it's equal to decline rate over time period. That's the definition. And we can use it for a software by it depends on the graph we have, so we will apply that. And D is constant only for constant percentage or exponential decline, because it's as we defined this in the exponential, it's a straight line, so the effective decline will be constant, but will be decreased for hyperbolic or harmonic when we change the B, because B factor is affected by the curve changes. It's easy to convert from a nominal decline factor to effective decline factor by using softwares, and we will see that how can we work with nominal and see the values compared then with effective decline. Nominal, it may be can apply it for monthly or yearly. Also, effective can be applied for monthly or yearly. It depends on the production, the data, and the result we need. The effective decline of 10% per year is equivalent to a nominal decline of 10.5 4 per year. That's the formula for this method. Yeah, we can change it or nominal, or we can use it for effective. And there is the percentage of 10% per year equivalent to this values. And there is another type of decline. That the first is exponential, and the second one is hyperbolic. Hyperbolic, here we have a b factor, so because the hyperbolic, we will see that in the plot, the curve is not a straight line, so we have a value of b, because b that's control the curve. So it's have a range between 0 to 1 and maybe higher than 1. We will see. So we have in this equation we need to use b. That's if we have a b, that means you have to add that in the software to give us a good indication. And we will see how can be control and help me to match the data with the curves. The data we needed are the same. We need the initial production rate and the initial decline rate. The initial decline rate can be changed and with regression after matching the data. So this is a variable, but this is a constant. Depends on the initial rate we have. In some analysis here, we for most conventional analysis, b is between 0 to 1. But in some cases, maybe b will be more or higher than 1. And here's the note: decline rate is not a constant. Yeah, it's a change with the time, and that's because the curve is changed. And after integrate this part, we can get a cumulative production for the next cumulative oil production by using this method for the future for the cumulative production to the forecasting. The B factor, it's without units, and normally it's a hyperbolic constant called sometimes. It's as we said in a range, and we can apply this hyperbolic method for oil or gas wells. It's generated from the general equation for B, and we can apply it for Q versus time as the same in exponential. We will see that in the practical training, and here we have some important point. The value of B has large impact in the late time. It will be lead to the different estimation of ER. That's mean the ultimate recovery, the ultimate reserves. Here in the late time, and we will see that in the practical. If we can see at the initial time, it's dropped like straight line, but we can see changes here. The curve is not constant at each step. So that's why D effective decline will change it. So B, it work with us in the last time here. Maybe in the first times here we can see as a constant, and maybe it will show as a straight line as an exponential method, but that will be different if we have a different curve here. So the B must be changed, depends on the late time, and have more effect on that, and will give us a different estimation of reserves. And B value increased with maturity of production data, that available B and large number of physical, because it's if we have a high effect and we need to adjust more data, so we need to use a B much higher than 1 to match our data here. If we can see here, that's the application by O of M, and we can see the value of B it's used 0.4. It's by user. We can use it by user or by auto of best fit to give us best value and optimization value for our B. Depends on the best match. We can see here this window is available in OFM, and after we apply the best method for auto, we can see the best matching here. We can see the phase is oil. Solution, the type of decline is empirical. We have some different methods for declines, and the analysis is rate here in log and the time. And for type of decline rate, as we use a monthly nominal, we can change that for effective. And the history match, the type of decline is hyperbolic. Here we have a b value. So b value, maybe we can enter it by user, or we have a range, or can be depends on the best auto method. It depends on the best matching here. Will give us an optimum value. The result will show here, and we will see that. And the last type of decline curve analysis is harmonic decline. Harmonic decline here, the b must be equal to 1. So after apply b for the general Arbus equation, it will give us this equation here with the changing in nominal decline. And we have initial point and the time, that's the cumulative time with prediction. After integrate this part, we can get a cumulative oil or cumulative fluid by applying this method. It's a simple formula, we can use it, and also it gives us a straight line here, but with different case, depends on the method, or depends on the data you have. In general, all of them have some other different technique for decline curves. By Arbus equation, we will work with empirical method. That's the last 3 types of curves, and there is another 3 different types. It's Vitkovich type method, and the analytical transient method, and local and Swire type curve method. These other different methods give us a good more data, more information. For example, Vitkovich, can we calculate by this method calculate another different reservoir properties, area and porosity and others. So we can use some of them or all of them to give us a complete vision to our reservoir. And to determine the type of decline, here's the base. After we talked about that, the decline curve analysis need to be more focused about these important things. One is the most representative period in history that will also represent future. That's the first assumption we talked about. And the second point is the decline tends during the period. The starting point, always we need we have to determine when we start our forecasting the production initial oil rate or gas or water, depends on the phase. And number 4, the constraints under which the forecast needs to be made. Yeah, you have to before you generate your forecasting, you have to see the constraints you want to work with. That's the most important recommendation before applying the forecasting to the future. The main use of decline curve analysis is to estimate the reserves and apply the history matching. For this method, we need to add some different techniques to determine determine the reserves. So always before decline curve analysis, we have a period to use a material balance and the reservoir simulations. These methods give us a good value for reserves, but we have some uncertainty because due to data. So the decline curve analysis can must be agreed with these methods. So decline curve analysis is normally made to give an increased confidence in our numbers from simulation or other method. And the application of constraints in the production system, and also we need to be more sure about the operating costs and the capital. All of these must be factors. These must be added to in our project to get good estimation reserves. We have to know some important things here. What's the meaning of reserves as we define it? That's the quantity of hydrocarbon which can be produced economically and commercially from our reservoir or wells. So the factors we need to be focused on, that we have two economic condition and technology available. So the reserve is always a dynamic values, so it's a change with time and change with the technology available. So what we can produce it economically with the technology available, that will be called reserves, and if not, that's maybe the reserves but undeveloped. We have two types of reserves, developed and undeveloped, and also depends on the economic condition. For example, the price of oil, and sometimes the reserves is reduced because when the price of oil reduced the costs, so that cannot be produced more oil because it will not give us more profit from these values. And we can see here in this life cycle of the reservoir estimation, that's the very important thing you must see, and we will see where we start apply the decline, and we start other methods. So the first point is A here before we start discover our reservoir or total field. Before we start that, we have a period of pre-drilling protection. Here we can get more analogy, and we can determine the reserves, and that's the high range of estimation for ultimate recovery. And at this time we still don't produce any production from our field. And from B to C, here we can see at this time development period is started after the exploration and appraisal. So after we get more data after we drilled some wells, so the uncertainty reduced, we can see here range of recovery estimation. But in this time we can see here it's high rates. We can start it from initially after we start the production, then continue some time at this time, and then reduce it. We can see this decrease in the production rate here where we can apply the decline curve analysis, not in this time, and that will take some years to wait until the production dropped in our reservoir. So if this time we cannot apply decline curve analysis in this period. Why? Because the production is increased, so in the decline we need to see more clear the production dropped. So we can see here in volumetric in this time we can apply it, and also performance of material balance and simulation here we can apply it, and we can see the decline curve trends analysis. We can use it here in this time after the production. In this period after start the production, we can apply material balance, because material balance also need the production and PVT, and we can use them here. And about the risks here, initially we have high risk for the company which is discovered and work with this field. but decrease it with increase the production. That means we have more reserves and we can produce it more, and decrease it more and more because we can see and we can know, depends on the decline curve analysis, we can forecast to our future when we stop the production, or when we can reach to the end of the life, depends on the decline curves here, which is give us a good indication at time and how much oil can be produced in the future. So that will be a good information for the company and reduce the risks. The reserve classification, we have three types of reserves: proven reserves and probable reserves and possible reserves. What's the mean of each number for each value here? Proven, that's which is discovered, and developed, which is the high value for us for the reserves which can be produced, and the drive mechanism defined. And it's called reserves because it's a current economic condition existing for at least 90% of reserves can be produced. And the probable, which is discovered but undeveloped. The mean of undeveloped means we have some reserves, but we cannot produce it right now due to maybe the facility and the surface. We don't complete the production surface protection system, pipes or separator, so we have reserved. But when we after complete the field development plan and the period, and we start the production, we can define it as a reserves. Proven and improved recovery also. For example, if you apply, that depends on the drive mechanism available, that's maybe natural, so we can get a good result for the proven. But if you plan to use another secondary recovery, water injection, water flooding, so the reserves, it will be changed here, and it will be probable because we need to use another different technique that will be high cost. So the probable reserve means we have a chance of hydrocarbon can be produced, but at least 50% we can be produced. And the possible reserves that's discovered also undeveloped, but restriction using high technology. Maybe we need to use EOR and traditional recovery, and this type of technology, it's very high cost, and that's we call the reserve is possible because we cannot reach to the at least 10% of hydrocarbon in the reservoir due to high costs here. So that's the possible, but cannot be proven, which can be produced. It depends on the technology we have and the ability of using our economical condition. But here we need to add some changes so we can get a good vision if we need to use another different technique with high cost, so the less reserves can be found, and that will be high cost because all of the reserves depends on the economic condition.